Today our presentation is about the MPPT and the ion charging system for the solar system. And here's our team members.
I'm Ben Gert.
I'm Sikiva.
And I'm Xiaotian Lu.
We have three main parts of our project that we're going to present about today. The first is the MPPT, the maximum power point tracker. The second is the charging system to charge the battery. And the third is the PC monitor application. And finally, we'll go over our roles and responsibilities.
So why we're making a MPPT controller for our project? Here's the thing. And you can see for solar panel, there's a PV characteristics. And you see if the voltage is really high and the current is really high, you won't get the very high power. So our MPPT stuff is pulling out the maximum power. And you can see this line. And so our essential idea for the MPPT stuff is the boost converter. We're using Arduino Uno for PWM input to the MOSFET to change the duty cycle. We're working at 31.25 kilohertz, like that, so that the inductor and capacitance will have very moderate numbers. We're having 7 1 watts and 10 volts solar panels to be our input. So we're having maximum input current to be 0.8 amps and maximum input voltage to be 10 volts. There's very big issues for us to sense the current voltage. Our original plan was to using Hall effects. It is using a magnetic way to get the current for that. So, but it doesn't quite work because it will be affected by other magnetic flux components. So our final decision is using shunt series circuits to be our essential method, and the voltage divider is measuring the voltage. Also, for the input to the boost converter, we're calculating the voltage and the current, their product, to get the power. And after that, we pass the power with analog signal into the microcontroller to analyze that.
So once we have these values in our firmware, these current voltage sense values that Xiaotian was talking about, we have to actually find the maximum power point using an algorithm. So just to further explain the MPPT, we have a full range here of a power input with duty cycle from 0 to 100%. So you can see the power go low to high to a little bit lower, and then the maximum duty cycle was found at 74%, so it keeps at that range. This isn't practical in use because we want the algorithm to adapt to changes in the solar intensity and inputs, whatnot. So common practice is to implement a hill climbing algorithm. We tried a few of those, including perturb and observe, but we found that they oscillated too much at the maximum point. And so, although they're very fast, they oscillate. So we decided to implement our own to sacrifice a bit of speed to reduce those oscillations in the final output. So our algorithm would, once setting the duty cycle, would change it 2% on either side to see the power on those two increments, and set the duty cycle to the maximum of those three. So you can see with our algorithm on the side, it oscillates a little bit, but less than perturb and observe algorithms that we implemented before. So again, the challenges are the oscillations, the speed, and then the integration with the sensing and the rest of our Bluetooth, our Arduino firmware, including the Bluetooth.
Here is the charging part. We just use the line charging for our circuits. And why we just use line charging? Because to compare with other charging parts, the same size and same weight, but the line charging has the better capacity, and it also has the full different stage from the constant current and the saturation charge, and the no current and the standby mode. But we have the difficulty in just designing this circuit because the we just rely the battery's full capacity without overcharging it. It may be difficult to analyze on the stage 4. And for my part, I just use the line battery by the transfer, and it can constantly provide 3.7 output voltage and 6.5 output current. And I use LM317 as the positive voltage regulator. It can supply 1.25 voltage to the 30 voltage, and the constant current around the maximum is around 1.5 amplifier. And for this part, I just think about use the 7805, but it just does not work very well. And for this one, it has better internal short circuit current, limiting thermal overload protection and output safety area compensation. Here is my circuits. The first one is the constant voltage circuits. I just use the 100 ohms and the 240 ohms to control the voltage regulator to provide a constant 4.25 output voltage. And the second one is the current regulator. I use the 5 ohms resistor to provide 0.25 amplifier in order to for our circuits to charging the battery. For the whole design, our original plan is just use buck converter, but as we just designed this one, it does not work very well because the input current is very low, so we just does not have very high efficiency. So we changed the plan to battery measurement, and I just want to use BQ24314, but as I talked with the professor, the chip is difficult to fit in the whole circuits. So we just give up all the plans and decided to use a voltage regulator and current regulator, which we can control the two-state charging by the software, but it still exists a little bit of problems in the efficiency.
The point between constant voltage and constant current in Li-ion charging is really hard to define. So what we do for this part is I built a column counter over here. It has an amplifier of 10 to get the voltage across a small resistor so that I can calculate the current through the battery. So it passes to the microcontroller to analyze the data of the current in times so that it can get the capacity charged into the battery. And then after it analyzes the data, it will pass it to a mechanical relay to switch between constant voltage and constant current.
So the algorithm firmware for this two-state switching, there's two parts. So the first is when you're charging the battery, you need constant current charging, and once you have to detect the switching state when you need to switch to constant voltage charging. So once a minute, we would check these two states to see which current was lower. So if it ended up being that constant voltage charging current was lower than that of constant current, then we would switch the states. So in the firmware, this is implemented in 1 second timer overloads, counting to 60. Again, the challenges with the firmware overall is just integration with the rest of the things that we're doing, which is quite a bit actually with the Arduino. So the final part of this project was the PC monitor application. So we will be wirelessly communicating with the computer from this MPPT system to monitor everything that's going on with it. So you see the inputs, the solar intensity, the output, which is the power generation, the state of the Bluetooth, as well as the battery charge using Xiaotian's cooling counter. We designed this to be user-friendly with minimal interaction from the users. You can see there's only 2 buttons, and one of them is disabled on the screen. And this pretty much just parses and displays the live data. For the wireless, we used Class 1 Bluetooth module, which has a 100-meter range. On the firmware side, we had the Bluetooth library from Arduino, and on the Windows side, we used the virtual serial ports that Windows creates for a Bluetooth connected device. The big challenges with this were WinForms is not ideal for displaying lots of data simultaneously. So we're getting data in pretty quickly to this interface, and updating the GUI elements associated with those data is is complicated, and oftentimes the programs crash if things are coming in too fast. The complications with the wireless communication is Windows creates 2 virtual serial ports when a device is connected. One is for external devices connecting to the computer, and one is for the computer connecting to external devices. And detecting which one was the one you needed to use required a little bit of problem solving, but eventually we solved that to be able to automatically detect which COM port to use to connect to our system. Here's just an overview of the roles and responsibilities that we've just talked about. But we can take any questions now if you guys have them.